All right, in this video, I'm going to discuss example 9.16 from the free online introductory statistics textbook, which you can download via this link. And this is a hypothesis test for the mean, and we have a greater than alternative hypothesis. Okay, so let's go ahead and read through the example first. So statistics students believe that the mean score on the first statistics test is 65%. Okay, so that's what the students believe. They believe it's 65%. The instructor thinks that the mean score is higher than 65%. Well, the instructor has access to all of the data, so he could just look at them all, but maybe, he wants to create some sort of exercise for the students, so he doesn't just look at them all, but he go ahead and he samples 10 statistics students. So he samples 10 statistics students, and he attains these scores, these 10 scores here. Okay. Then he performs a hypothesis test using the 5% level of significance. So 5% level of significance, that's important. All right. The data are assumed to be from the normal distribution. Okay. So we're going to go ahead and do this hypothesis test. So step 1 is to write our hypothesis, the null and alternative hypothesis. Okay. And first off, are we talking about a proportion or are we talking about a mean? Well, we're talking about the mean, right? We're talking about mean score, the mean score. The instructor thinks that the mean score is higher than 65. So we're talking about the mean score here. Okay. So since we're talking about a mean, we're going to use mu. Both the null and alternative hypothesis will have mu. Okay, the null hypothesis always has the equal sign. Always, always, always. Okay, so what am I going to have equal? Well, what are we testing? We're testing something about this 65%, right? So the null hypothesis will be equal to the 65. Okay, and since the 65 is there in the null, the 65 will also be in the alternative. That number must always be the same. What you have here must always be what's here. Okay, now what's the sign? Is it greater than? Our choices are greater than, less than, or not equal. Okay, we have 3 choices for the alternative hypothesis. Okay, so let's see. The instructor thinks that the mean score is higher than 65. So the mean is higher. Okay, so higher mean the alligator eats the mean, right? It eats the higher. So higher than the mean, so it's the greater than symbol. Okay, mu is greater than 65. Okay, now, step number 2 is to calculate our test statistic. Test statistic. For mean, we have 2 different test statistics. Okay, so ZT could equal x bar minus mu divided by sigma over the square root of n. Or you could have the test statistic equals x bar minus mu divided by s over the square root of n. They're very similar. What's different about them? Well, this one I have sigma, and this one I have s. All right, and this formula up here, you would need to know something about the population parameter. Remember, what is sigma? Sigma is the population standard deviation, and s is the sample standard deviation. Okay, and we can use the population standard deviation, even if we really only have a sample, you can go ahead and use this top formula as long as n is greater than, say, like 30. If n is large, then you can go ahead and you can say, oh, my sample standard deviation is close enough to population when I have a large sample size, so I can go ahead and use this. Otherwise, when your sample size is less than 30, go ahead and you want to use this second formula I have down here. Okay, so if you're using this second formula, we need to remember that this is the t distribution, or the student t distribution. Okay, and so this is the student t distribution. And if you use the top formula where you have sigma, the population standard deviation, then you have the z distribution. Okay, and that comes into play again when you're doing your p-value. All right, and I'm going to talk more about that. So we just remember that we have the t distribution because we have a small sample size. And so when we're doing our p-value, we're going to need to use the t distribution, not the z. Okay. All right. So let's see. Let's go ahead and calculate this. So I have x bar minus mu divided by the sample standard deviation over square root of n. All right. Well, one thing I can plug in is mu, because mu is always going to come from the null hypothesis. That's why the null hypothesis has to have this equal sign. So instead of writing mu, let me erase that. I'm going to write 65. Okay? That always comes from the null hypothesis. Always, always. Now, what is x bar? Well, they gave me the data, so I can calculate the sample mean, but I don't know it yet. S, also, they gave me the data, so I can calculate the sample standard deviation, but I don't know it yet. N, what's the sample size? Okay, we have 10 students. There's 10 data points if I were to count them up. Yep, 10 data points, so that is 10 here. Okay, so let's go to Excel and let's calculate the sample mean and sample standard deviation. First thing, I'm going to go ahead and just write down these 10 values. So I have 65, 65, 70, 67, 66, 63, 63, 68, 72, and 71. Okay. Double check that you copied them correctly because this is an area where students often make mistakes, understandably so. Okay. Data entry is not that easy. Making sure that you have copied your data correctly is very important though. Okay. So first thing, x bar, which is the sample mean. Type in average, open parentheses, and then highlight all your data. Okay, so it goes from A1 colon means you continue going until you get to A10. Close parentheses, press enter. 67. Okay, S, the sample standard deviation. Standard deviation. STDEV dot S. Okay, you see dot P, that's for population, dot S is for sample. Okay, highlight all the data. Okay, A1 through A10. Close parentheses, press enter. 3.1, well, if I were to round that 7, that 9 goes to a 0 and makes 3.20. 3.20. All right. Next, I can actually just use Excel to calculate my test statistic, Z. I could just use a regular calculator, but if I have Excel open, it's nice and easy. So type in equals, open parentheses, okay, x bar, I could write 67, or I could just click on that cell, C1, minus 65, close parentheses, divided by, now make sure you use parentheses for both the numerator and the denominator. So I have parentheses for the numerator, or the top of that fraction, and I have parentheses for the bottom of the fraction as well, okay? So S, so I'm just going to click C2, as opposed to typing out all that decimal or having rounding errors. Okay, C2 divided by SQRT of 10. Okay, the sample size is 10. Okay, close the parentheses for the square root, and then close the parentheses once again for the denominator, or the bottom of the fraction. Okay, press enter, and we get 1.9, if I were to round that to two decimal places, that 8 brings the 7 up, so 1.98. Okay. So my test statistic, ZT, equals 1.98. Okay. All right. Once you have your test statistic, step number 3 is to calculate our p-value. All right. What is our p-value? And remember, I said if we use this formula, our sample size is small, then we're going to need that t distribution for the p-value. Okay, so this is where this comes into play. Okay, so t distribution looks just like a normal distribution, or the z-distribution looks the same, centered on 0. Okay. My test statistic, where is my test statistic? 1.98 is higher than 0, so it's somewhere over here, 1.98. All right, and our p-value is always 1.98 an extreme value. That's basically what you're trying to ask yourself. And extreme is based off of whatever the alternative hypothesis is. All right, so our alternative hypothesis is greater than. So greater than means more, right? So more, I'm going to want that right-sided tail. So this is a right-tailed test. Okay, because of that, greater than in the alternative hypothesis. Okay, if it was less than, then we would have had a left tail test. All right, so it's greater than, we have a right tail test. All right, so I basically want to know, what is this area? That is what the p-value is. The p-value is this area I've highlighted here in blue. And this is a t-distribution. So basically, this is the probability that t is greater than 1.98. All right, and I can figure this out in Excel. So let's go to Excel. And my p-value equals t dot dist. Okay, open parentheses. All right, first thing it asks for is what is the x value, or basically what are you trying to calculate the probability for? That's that 1.98. 1.98. Okay, the degrees of freedom. T-distributions always have degrees of freedom. Degrees of freedom is always the sample size minus 1. So what's our sample size here? It's 10. So 10 minus 1 is 9. Okay, and then you always write true for cumulative. But what does true find? Right? What is cumulative? What is cumulative? Cumulative distributions will always give you the less than probability. Okay? Or in other words, it'll give you the probability that t is less than 1.98, which is this area I'm marking here in red. Okay. So if I want the area that's in blue, then what do I need to do? All right? Remember, the total area under this curve, the total area under the curve is 1, right? So the probability that t is greater than 1.98, or that blue probability, is going to equals 1 minus this red probability, the probability that t is less than 1.98. Okay? Less than 1.98. Okay? So when I put this into Excel, I need to write 1 minus this t distribution. Okay, so let me write 1 minus out front. Okay, and that's always the case when you have right-sided test. You're always going to have 1 minus out front. All right, press enter, and there we go. 0.0, if I were to round that off, 0.04. Right, the 9 brings the 3 up, so 0.04. So this blue area equals 0.04. Okay. All right. I just want to mention here, if I were to use this z-distribution, the only thing that would have been different is instead of using t-dist, I would have used that formula, what is it? Norm.s.dist. Okay? And then there's no degrees of freedom, so I would have erased that. Okay? So my p-value would have been different. See, it's 0.02 if I had a large sample size and I was using this formula here with sigma. Okay? Because I have a small sample size, I can't use norm. I can't use the normal distribution. I can't use the standard normal distribution. So I need to use the t-distribution, t-dist. Okay? All right, degrees of freedom, remember, is always, let me write this down. Degrees of freedom equals 1 minus n. So in this case, that was 1 minus 10, which is 9. Okay, so what is my p-value? Right, we calculated, press enter, 0.0395, which rounds to 0.04. Okay, let me write that down here. My p-value equals 0.04. All right, step number 4. We need to say something about the null hypothesis. Are we going to reject the null hypothesis, or are we going to fail to reject the null hypothesis? Okay, so which one are we going to do? Okay, this has something to do. Let's go back up here. So remember, we assumed the null is true when we calculated our z statistic. So we assumed it was true right here when we plugged in for mu equal to 65. Okay, so the question is, was that assumption reasonable, right? So if that assumption was reasonable, then our test statistic, this 1.98, would not be an extreme value. Would not be an extreme value. So we would have, if this is reasonable, then there would be no reason to reject it. So we would not reject it, and this value is not extreme. All right, but if it's not reasonable, if this assumption, this plugging in, was not reasonable, then this 1.98 is an extreme value. Well, how do we know if 1.98 is an extreme value? Well, if this probability, this blue probability over here, if this is very small, then 1.98 must be an extreme value, right? So basically, how do I know? Is it small? Is 0.04, right? Remember, we figured out that this area here in blue, this is 0.04. Is 0.04 a small value? Is that 1.98? Is it extreme? Okay. So we will reject the null hypothesis whenever the p-value is small. It's less than what? Less than alpha. Okay. Less than alpha. What is alpha? Alpha is the significance level of the test. And then we're always told that in our original question. So the significance level is 5%. So alpha then is 0.05. Okay. So let me write that down here. So the p-value, 0.04, is less than 0.05. Is that true? The p-value is less than 0.05? Yeah, that is true. So we are going to reject the null hypothesis. Okay, obviously we would have failed to reject the null hypothesis if the p-value was greater than alpha. But we will reject it when our p-value is very small, when this 1.98 is extreme, and it is extreme. Okay? That area beyond 1.98 is very small, so it's an extreme value. So we have rejected the null hypothesis. Okay? So our last step is to say something about the alternative. If we've rejected the null, then the alternative, there's reason to believe the alternative may be true. Okay? So that's our last step. So step number 5, there is evidence to suggest that the mean score is more, right, or higher than 65. All right, which is basically what the alternative said, right? The alternative said that mu was more than 65. So I just kind of rewrote that in English. So there is evidence for the alternative because we've rejected the null hypothesis. Had we failed to reject the null hypothesis, then there would not be enough evidence, or there is not enough evidence to suggest that the mean score, so not enough evidence to suggest that the mean score is more than 65. Okay. But because we did reject, okay, that's our final answer.